JWST detects strong evidence of a thick atmosphere on lava world super-Earth TOI -561b, a rocky planet that should have been stripped bare, appears to be holding onto air. New observations from the James Webb Space Telescope point to strong evidence of a thick atmosphere on TOI -561b, an ultra-hot lava world super-Earth that races around its star in under 11 hours. It matters because this is exactly the kind of planet most models say should not keep an atmosphere for long. If TOI 561b can, then the line between airless, rock, and atmosphere-bearing world is blurrier than expected. The immediate tension is simple. The planet's dayside looks cooler than a bare rock should look at that distance from its star. Something is muting the heat signature. The leading explanation is a thick, volatile-rich atmosphere moving heat around and absorbing some of the planet's infrared glow. But the details of what that atmosphere is made of and how it survives are still unsettled. This piece explains what Webb actually measured, why scientists think it implies a substantial atmosphere over a global magma ocean, and what needs to happen next to separate competing scenarios. The story turns on whether TOI 561 billions is too dim. Infrared signal is best explained by a durable, volatile-rich atmosphere. Key points. JWST observations show TOI 561b's dayside emission is inconsistent with a bare rocky surface, strengthening the case for a thick atmosphere on a rocky exoplanet. The planet is a super-Earth with an ultra-short orbital period, less than 11 hours, and is likely tidally locked, with a permanent dayside and nightside. The signal comes from watching the system through repeated secondary eclipses, isolating the planet's contribution to the light. The dayside appears cooler than expected for airless rock, implying heat redistribution and/or absorption by gases and possibly clouds. The atmosphere's exact composition is not pinned down yet. Volatile-rich is the key point, not any single molecule. Follow-on analysis aims to map temperatures around the whole planet and narrow which atmospheric models can fit the full dataset. Bowed TOI -561b is a super-Earth, meaning it is larger than Earth, but smaller than Neptune. It sits in a rare category called an ultra-short period planet, worlds that orbit so close to their stars that a year lasts hours, not days. These planets are expected to lose light gases quickly under intense radiation, leaving behind exposed rock, or in the most extreme cases, a thin veil of vaporized minerals. A lava world is the natural endpoint of that idea. With enough heat, rock melts. On TOI 561b, the dayside is expected to be hot enough to sustain a global magma ocean. The planet is also likely tidally locked, a common outcome for close-in orbits, so one hemisphere is locked under constant starlight while the other sits in darkness. Webb can't take a direct picture of TOI 561 billions. Instead, it measures light very precisely. In this case, the crucial technique is the secondary eclipse. The planet moves behind its star, and the total light drops slightly, because the planet's own glow and any reflected light is briefly hidden. By comparing planet visible to planet hidden repeatedly, scientists can reconstruct the planet's emission spectrum. The new result matters in part because rocky planet atmospheres are hard. Hot Jupiters and warm Neptunes have big gaseous envelopes and strong signals. A rocky planet's atmospheric signal is smaller, and on an ultra-hot world it is tangled up with surface emission, heat transport, and clouds made of exotic materials. Analysis technological and security implications. This is a showcase for how JWST studies rocky planets at the edge of what is measurable. The data come from time series spectroscopy in the near-infrared, focusing on wavelengths where a blisteringly hot surface should glow strongly. The planet did not cooperate with the simplest expectation. It looked dimmer than bare rock models predict, and that mismatch is where the atmospheric inference comes from. The next technical step is harder than the headline. A single dayside snapshot can tell you something is off. It cannot fully tell you what the atmosphere is. The real prize is a full orbital phase curve, watching the planet brighten, dim across the entire orbit, to infer how heat is redistributed from day to night. If winds are hauling energy around the globe, the day-night contrast shrinks. If the atmosphere is thin or absent, the dayside stays brutally hot, and the night side stays cold and dark. There is also a subtler implication as the community pushes JWST towards smaller and harsher worlds. Model security matters as much as instrument sensitivity. Different assumptions about surface reflectivity, cloud brightness, and gas absorption can produce similar-looking spectra. The science will hinge on whether multiple independent modeling approaches converge on the same conclusion once the full dataset is in hand. Economic and market impact. Webb time is a scarce resource. A result like this increases the incentive to spend more of that resource on ultra-short-period rocky planets, not because they might be habitable, but because they are natural laboratories. They let researchers test how atmospheres form, erode, and possibly regenerate under extreme stress. There is a downstream funding logic, too. When an observatory produces a result that overturns a common assumption, it tends to reshape priorities, more proposals, more follow-ups, and stronger arguments for future missions designed to characterize Earth-sized planets in detail. The value isn't only in one planet's atmosphere. It's in the possibility that a whole class of worlds has been mischaracterized as airless when some may still carry thick envelopes. Social and cultural fallout. The public-facing story will be tempted toward one word: atmosphere. That word pulls people toward life, even when the actual planet is closer to a molten furnace than a second Earth. The more honest hook is different. This is about how planets work, not whether anyone lives there. Still, the cultural impact is real. A rocky planet with a likely magma ocean and a thick atmosphere is vivid. It gives educators and communicators a rare, concrete example of alien geology that is not speculative concept art alone. It also reframes the narrative of exoplanet discovery from counting worlds to reading worlds, where small differences in starlight reveal physical processes on a planet hundreds of light years away. Political and geopolitical dimensions. Webb is an international flagship, and results like this are part science, part soft power. They reinforce the value of long-horizon investment, international partnerships, and shared data pipelines. They also sharpen the competition for who leads the next phase of exoplanet characterization, where the question is no longer, is there a planet, but what is it made of, and how does it evolve? There is a more pragmatic political angle as well. Atmospheric studies of rocky planets are often used to justify future mission architectures. A strong, widely discussed result on a rocky world makes it easier for agencies to argue that the hardest measurements are not science fiction. They are simply expensive and difficult. What most coverage misses. Most quick takes will treat thick atmosphere detected as a binary. The reality is a hierarchy of claims. What is strongest is the inconsistency with a simple, bare rock picture at the observed wavelengths. From there, the interpretation becomes model-dependent. A thick, volatile-rich atmosphere is the best fit, but clouds and surface properties can complicate the reading. Bright silicate clouds, for example, could reflect starlight and cool the dayside, while also changing which wavelengths escape to space. The second, overlooked point is survivability. Even if 2I-561b has a thick atmosphere today, that does not mean it held onto a pristine primordial envelope for billions of years. It could be replenishing the atmosphere through continuous exchange with a magma ocean, outgassing volatiles and reabsorbing them, reaching a dynamic equilibrium rather than a one-way loss to space. That's a fundamentally different picture of atmosphere retention than the standard story of gradual stripping. Why this matters. In the short term, the people most affected are scientists trying to interpret rocky planet signals, and the agencies deciding what Webb should look at next. This result raises the odds that more ultra-short period rocky worlds will be targeted for deep phase to curve campaigns, because they stress test atmospheric physics in the most unforgiving conditions. In the long term, it touches the broader search for habitable planets in an indirect but important way. If small planets can keep or rebuild atmospheres under extreme irradiation, then atmosphere loss may not be a simple filter that rules worlds out. That does not make 2A-561b habitable. It changes how confidently scientists can label other rocky planets airless when the data are sparse. What to watch next is not a press conference. It is whether the full orbit analysis shows a clear day-to-night heat transport signature, and whether additional wavelengths support the same atmospheric models. If the temperature map and spectra line up, the atmosphere case strengthens. If they don't, clouds or surface effects may move back to center stage. Real-world impact. A science teacher in Manchester updates a lesson plan the next day. Instead of rocky planets close to stars lose their air, the class debates 3 possibilities: loss, survival, or constant recycling through molten geology. A small aerospace supplier in California that builds components for infrared instrumentation uses the headline in a pitch deck. The argument is straightforward. Precision infrared measurements are not abstract. They change what humanity can know about other worlds. A data scientist in Bengaluru who works on time series anomaly detection reads the method's thread and recognizes familiar problems: tiny signals, correlated noise, model uncertainty. They spin up a hobby project to learn phase curve fitting techniques because the frontier looks surprisingly transferable. A policy analyst in Washington working on science budgets sees a clean narrative forming, investment paid off, and the next step is even harder. They start tracking how often rocky planet atmospheres shows up in mission justifications. Significance. TOE 561b is not a candidate. It is a stress test. A rocky planet so hot and close in that it should be losing gas, yet it appears to be wrapped in a substantial atmospheric blanket. The fork in the road is whether that blanket is truly thick and volatile-rich, maintained by global circulation and magma-atmosphere exchange, or whether clouds and surface physics can mimic the same dimmed infrared signal without requiring a long-lived atmosphere. The trade-off is not philosophical. It is measurable, but only with more modeling pressure and more complete orbital information. The clearest sign the story is breaking one way or the other will be a consistent global temperature pattern that demands strong heat transport, plus spectral behavior that stays aligned with volatile-rich models across the full orbit. If those pieces lock together, the air on a lava world claim becomes a new reference point for rocky planets everywhere.